So this is the intro to our acid-base unit. We'll go over what they are and how to identify them and a little bit about some other stuff. But let's start. So acids and bases. Acids, they taste sour and they sting when touched. Normally we wouldn't eat chemicals, obviously, but there are some acids that are edible, like citric acid, which is found in, lemons and limes and that type of things. Vinegar, same thing. It's an acid that we can eat. But in general, we don't eat these things. Acids give off H plus ions, and H plus is also known as a proton. It's called a hydrogen ion. They are found on table K, and they start or end in H. Basically, if they're not on table K, then as far as you're concerned, they are not an acid. Now, not everything that starts or ends with an H is an acid, just basically what I just said. So for example, H2O is not an acid. NaH, it gives off a hydrogen ion. That is true. It gives off an H minus though, and an H minus is not the same as an H plus. Also, another way of talking about an acid is calling it a hydronium ion. A hydronium ion is H3O plus. It is a temporary hydrogen ion storage molecule. Basically, when an H plus happens in water, it forms H3O plus, which is like a temporary molecule. So basically, hydronium, hydrogen, or proton, it all is talking about acid. Let's do bases. Bases taste bitter, feel slippery when touched, like soap. That's because bases are used in soap, although not so much very mild bases are used in soap. Let's put it that way. Nothing that's going to just kill you or anything like that. They give off OH minuses called hydroxide ions. Bases end in OH. They are only found on table L. So not everything on table L is a base, and as far as you're concerned, only the things that are found on table L are a base. An example, NaOH, it's found on table L, it's a base. CH3OH, it is not found on table L, it is actually an alcohol, we would find it on table R. What is the main difference between these two? What makes something a base and what makes something not a base? It's actually really simple. When NaOH goes into water, the OH pops off as an OH minus. When CH3OH goes into water, the OH stays on. And it's really because the bond between the Na and the OH is ionic, so it will dissociate, whereas the bond between the OH and the rest of the molecule is covalent in alcohol, and it won't. This is going to be more of a side note for now. We will come back to this, hopefully, when we're in school, but maybe not. Group 1 and Group 2 metals, when they react with water, they make bases. Just think of it as a fact for now. We'll get into the actual specifics of the reaction later on in the year. And now acids and bases. They can be we call it monoprotic, diprotic, and triprotic. In other words, they can give off 1H, 2H's, or 3H's, and bases can do the same thing. We call it monobasic, dibasic, and tribasic. They can give off 1OH, 2OH's, and 3OH's. Now, one thing I want you to look at when you compare these, acids give off H plus as their only positive ion in solution. That is what they all have in common. So no matter which base or which acid we're talking about, the positive ion is always going to be an H. The negative ion can vary, that part doesn't matter, but their positive is what they have in common. For bases, it's the reverse. In a base, the positive ion can vary, but the OH minus is the only negative ion in solution. The reason I'm stressing this so much is you're going to see these on CASA Learning, these types of questions. H plus is the only positive ion, OH minus is the only negative ion. Now, what do they have in common? Well, they're all electrolytes. So an electrolyte is anything that gives off mobile ions when dissolved in water, therefore it can conduct electricity. So up until now, we've said salts or ionic compounds are electrolytes. Salt is another name for ionic. We are going to add acids and bases to that list because they have that in common. They give off ions. Acids give off H pluses, bases give off OH minuses, and ionic compounds break up into plus and minus of varying types depending on the compound. So they all give off mobile ions when dissolved in water, therefore they all conduct electricity. We are going to summarize acids and bases for you up here. So there is 2 acid-base theories that you have to know of. There's actually a third, but we're not going to get into it. The Arrhenius theory and the Bronsted-Lowry theory. Now, Arrhenius is the scientist's name who discovered it, and same with Bronsted-Lowry. We're just going to call them the alternate theory. So, turns out the acid is the same. the Arrhenius acid gives off an H+. The Bronsted-Lowry or alternative theory says they donate an H+. But if you think about it, giving away an H and donating an H, it's the same thing. Okay, so donate and give away, it's basically synonyms, and so we're not going to make a distinction between their acid theories. Okay, but they differ in their base theories, which is why we have the two theories. A base is anything that gives off an OH minus. That's the Arrhenius theory. The alternative to a base is being an H plus acceptor. Think of it like in a sports game that has a penalty box. When a penalty goes against the opposing team, rather than giving you an extra player, they take a player away from the team that got the penalty, therefore giving the other team the advantage. And that is how it works. Now, in theory, you could do that as an acid. You could be a OH minus acceptor, and that would make you an acid in theory, but nothing does that, which is why we don't mention it. So here's a visual representation of the three theories. The first thing we always start with is the acid and the base levels are equal. In the Arrhenius or the alternative acid, they add H pluses to the solution. So what that does is it raises my H plus level, so now it's the green one that I shaded in, making me have more H pluses than OHs. That makes something an acid. In a base, we do the opposite. We just add OH minuses. That's the first base theory. So therefore, my OH minuses are going to outnumber my H pluses, and I'll be basic. In the alternative theory, what we do is we actually lower. They started out even in your notes, and what I did was I erased this or whited it out and shrunk down the H plus size. And so by removing H pluses, I give the OH minus the advantage, making it a base. And that's what makes the alternative base work. Okay, now, last part. It looks complicated, but it's not. It is called acid-base pairs. It is a continuation of the alternative theory. And here's how it works. You're basically going to be given these chemical reactions, and you're going to figure out which one was the proton donor and which one was the proton acceptor. The proton donor is obviously the acid. The acceptor is the base. So for this first one, all you do is you're going to look and you see what happened when I went from there to there and what happened when I went from here to here. Now, let's actually skip this first one because we'll come back to it. But for the second one, watch the pairs that I pick. Here I'm going to go H2SO4, and I'm going to pair it with the SO4. And then here I'll take the OH, and I'm going to pair it with the H3O, because basically you're looking to see what these compounds did. They either gained H's or lost H's. So in this case, I'm linking the SO4s together, and then I'm linking the other stuff together. The reason it didn't matter on this first reaction was because they were both H2O, so it doesn't really matter if I went from here to here or from this one to the OH minus. That won't matter. So now here's what you do. You look at the chemical and you say H2O, OH minus. What did it do in terms of H's? Did it gain an H or did it lose an H? Well, in this case, the H2O lost an H to become OH minus. Don't worry about the order. And therefore, the other one must be the H plus acceptor, okay? Because it went from H2O to H3O. Now, obviously, if we reverse the reactions, these would flip. We're not concerned about that. So the H plus acceptor makes this one the base, and the H plus donor makes this one the acid. And that's it. That's all you have to be able to do. So if we look at the next one, H2SO4 became SO4. So it lost two H's in this case. Whether we lose one or two or three, that actually doesn't matter. So H plus donor, that one was the acid. And the other one has to be the base, and it has to be the acceptor, because you can't do one without the other. So this is the H plus I'm going to go through the next three a little faster, and hopefully you can follow along. So again, here, since it's two H2Os, it doesn't matter if I connect, it doesn't matter which one I connect to, it won't make a difference. So I'm going to connect to whichever one is more convenient for me. So I chose those. If you chose the other two, it wouldn't matter. Your answers would still be the same. They would just be flipped. So H3O became H2O. That's the acid because we went from 3 H's to 2 H's. So the only way you can do that is by giving away one of your H's. That's donating, hence the acid. The other one, therefore, has to be the base because OH minus gained an H to become H2O because here they only had 1 H. Now they have 2 H's. Don't worry about the order. And therefore it accepted an H. The next one, I'm going to have to connect these two because they both have nitrogen in it, and then the other two connect. And then for the last two, I connect the SO4s because they have SO4, and the other two because they're H2Os. And then we figure out what they did. H plus acceptor, because it took in an H to go from 3 H's to 4. H plus donor, acid. And the last one, H plus donor, because it went from 2 H's to 1 H. That makes it the acid. And the very last one, H2O, became H3O, so it gained an H. H plus acceptor. That makes it the base. The only thing I did not mention, and we'll go over it right now, is this last bit here. On table K, when you look it up, one of the common questions is why is NH3 listed as a base if it doesn't have an OH to give away? Okay, so if you look, the base table, they all have OH in common, and the acid table, they all start or end in an H, and so they have that in common, but there's this one that stands out. Why is that a base? Well, the reason is because it's an alternative base. It is an H plus acceptor, and the way it does that is simple. NH3 can take on an H plus by accepting it, becoming NH4. Now that doesn't look like a base, but when you look at the entire reaction, what happens in water, it explains why it's a base. The NH3 in water gets the H plus from the water itself, turning the H2O into just OH minus as a result. So basically, NH3 produces OH minuses because it gets one of its H's from water, leaving it as OH minus, which makes it a base. So that is an alternative. That's what the alternative bases actually do. That's what was happening to pretty much all of these as a result.